In this video, we'll take another look at how we compare the two different existence and uniqueness theorems. So the main difference between these theorems is when they apply and what they sort of tell us when they do apply. So for the linear theorem, we are told that we have a solution, it exists and is unique so long as both p of t, the coefficient of y, and g of t, the right-hand side, are continuous. The theorem actually goes beyond that. It says that really the points where the solution can stop existing or stop being well-defined can only happen when either p or g has a discontinuity. And this fact here really comes from the fact that linear equations have a well-defined solution method that always works no matter what. Even if it ends up writing the solution as an integral, it still has a formula that works no matter what, provided we have a linear equation. And these integral formulas break down exactly where there are discontinuities of p or g. So if you want to find where a solution exists to a linear equation, you want to look at where the initial condition is, and then expand out until you hit the discontinuities of your coefficient functions, and that will tell you the exact interval on which your solution is going to be defined. And we'll see in some examples how that works and what that means for these solutions. Now, the nonlinear theorem tells us a lot less. First of all, it has extra conditions that both the function and its partial in y must both be continuous. And now these aren't just functions of t, they're functions of t and y, so it's continuous on some rectangle around the initial condition. Now the issue with this is we don't know what the solution is going to do once it leaves the initial condition. Right, say for instance I have an initial condition that is at some point here, and I know on this green rectangle it's continuous. Well, I could say, sure, as long as the solution remains inside that rectangle, then we know the solution will exist and be unique. That's fine. However, it's possible the solution from this point takes off like this. And so it leaves the rectangle before the edge of the interval in t. And so we can't necessarily say the solution exists all the way up to these sort of t endpoints because it might leave the rectangle before then. So all we can say is that it exists on some interval that very well might be smaller than the interval in t where it's continuous around this point. And there's no way right from the theory to know exactly what this interval is. To find out what that is, you'd have to actually go through the process and solve the problem, and then see where that solution is actually defined in order to get this interval. From the theory, we only know that it's on some interval around the starting point. We don't know what's going to be beyond that because we don't know when it's going to sort of break out of the rectangle to sort of violate these conditions at that point. So since we can't say anything, I'll say it's some interval around this point, and then we need more information from the actual problem, actual solution to go from there. And we'll see that in the examples that we work out for this section.